kids. Today we are visiting our local science and music program. Please join me and our musical volunteers on our journey of the periodic table of elements. Back to you, Ursula.
Everybody, I'm Ursula, and no, not the one from The Little Mermaid. I'm not that mean. Well, maybe a little. Anyway, I am a science genius, and today I want to share with you my very special secret weapon. That is going to help me, well, us, win today's scavenger hunt, and then I'll be queen of the world. Oh, we're still recording now. Sorry. Anyway, I also need your help, but it's okay, because we have a secret weapon. Known as, drumroll please, periodic table of elements. Exciting stuff, isn't it? So, the periodic table has many different patterns. The first being the increase of atomic number. As you can see, 1, 2, 3, 4, and so on. The elements are organized in this way because the atomic number at the top of each little element box represents that element's number of protons, which is the same number as its electrons. The basic outline of an atom, which includes protons, the positively charged part of an atom, which is located in the nucleus, along with the neutrons that have a neutral charge. So, you know that the number of protons and the number of electrons are the same as the atomic number. I know you're wondering, well, what about the neutrons? Don't worry, I got this. I am a genius. But I can't wink. So in order to find out how many neutrons, you must take the atomic mass, which is included in each element box, and round it to find its mass number. Then you need to remember how many protons, or the atomic number, of that element. Once you have both the mass number, which is the rounded form of the atomic mass, and the atomic number, which is the same as the number of protons and electrons, you must subtract. It's a lot, I know, but I know you're smart enough. Here, let's try one. Let's continue to do sulfur, which is element number 16. I bet I can count faster than you. Ready, set, go! 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16! Hey, you cheated! I guess I'll let you win this time. Already seen, this is sulfur's individual element box. And as you can see, the atomic number is 16. But we already knew that, because we pay really good attention. And we can see that the atomic mass is 32.066. So we already know that the number of protons and the number of electrons is 16. So now all we have to do is round 32.066 to just 32. This is our mass number. Then we must subtract 16, our number of protons, from our new mass number, which is 32. So 32 minus 16 is...
16!
Good job! It's 16. Crazy, right? Our number of neutrons might not always be the same as our protons and electrons. We just got lucky. This is what our sulfur atom might look like. In the nucleus, it has 16 protons, 16 neutrons, and on the shells, there are 16 electrons. But you may notice the electrons in the outermost shell, which are blue. These special electrons are called the valence electrons. They are only located on the outer shell, and some atoms have more than 3 shells, or more than 6, or more than 12, who knows? But the valence electrons are always on the very last shell of an atom. This brings us to our next set of patterns, families. On the periodic table, there are periods that run horizontal or side to side, and there are families that run vertical, up and down. Do you look or act like someone in your family, like mom, or dad, or grandma? I know I do, and believe it or not, so do elements. Elements in the same family share the same number of valence electrons. They also share characteristics, such as how they react, and sometimes what state they're in, liquid, solid, and gas. For example, this particular family is known as the inert gases, which include helium, neon, argon, krypton, xenon, and radon. We already know that families share characteristics and that each member of the family has the same amount of valence electrons. But what if scientists found a new element, element number 118? Let's call it myoson. All they would have to do to figure out what family it belongs in is to find its valence electrons, and it would react much like the others in its family. In this case, it wouldn't react, because inert gases are essentially happy.
meaning that they cannot give or take valence electrons or space on their shells from another element atom, because they are happy and complete. You probably tend to be happier when you're with your friends, right? Yeah, me too. Well, like us, so do elements. Which brings us to our next pattern. Very few valence electrons are located on the far left, and they are feeling very blue, because they don't have as many friends, or valence electrons, to join them or chemically bond with them. So they are highly reactive because they want friends, and they will mix with just about everyone who is willing to share. Then, we move more towards the middle of the periodic table, and those elements are sort of happy, sort of sad, because they have a few friends, but maybe not as many as they really want. So they are going to search for friends who share the exact same interests, and that will make them feel complete. Then we move to the right a little bit more, and these elements are also very sad, because they are missing that one or two friends that they can't live without, and they are just so eager to be with that friend that they will finally find them and just highly react with them so that they are happy. Then we move to our non-reactive elements, and they have no space on their shells because they already have all their friends, and all of their valence electrons are there. And they are just partying, like we will be when we win this scavenger hunt. There is one more pattern that is key to winning, and this is the squiggly line. And I know I sound crazy, but just bear with me, because I am a scientific genius. Okay, sorry. On every periodic table, there's that thick black squiggly line. And at first you're like, what the heck is that doing there? Maybe it's just for decoration. But it's not. It is our last puzzle piece. So basically, every element that hugs that black line, those green elements, are considered the semi-metals. And every element to the left of that line that doesn't hug it are the metals. And everything to the right are the non-metals. Okay, friends, it's time for our winning question. And since you paid attention that whole time, you're going to help me with this, right? Yay! I was scared for a second. I thought you might say no. So, our challenge is to find an element that is A, non-reactive, B is a semi-metal, C has 6 valence electrons, and D, only 52 protons. Let's think. Got it! Great job! It's tellurium! I couldn't have done it without you. And guess what? We beat our opponents! Holla! Thanks for joining me and helping me figure out this tough scavenger hunt. Now, let's go party like those inert gases with all our friends!